We're going to look at the link between the binomial and the normal distributions. A distribution that is binomial with parameters n and p is approximately equivalent to a distribution that is normal with parameters mu and sigma. We'll have to plug in formulas for mu and formulas for sigma. We know that for the binomial distribution, the average mu is n times p. So you'll use this formula to find mu. And we know that sigma is the square root of n times p times 1 minus p. And this is the formula that you'll use to get the standard deviation. You're allowed to say that this equivalence exists under the assumptions that n times p and n times 1 minus p are both greater than or equal to 10. N times p is your number of successes. It's the number of people who said yes. N times 1 minus p is your number of failures. Remember, in a binomial distribution, there are only two outcomes: yes, no, success, fail. So n times p is your measure of successes or yeses, and n times 1 minus p is your measure of failures or nos. Just to give you an idea of why these two are equivalent, the binomial distribution is shown in the histogram. A normal curve has been fitted over the binomial distribution. Notice that in some places there are gaps where the curve overestimates, and in other places the binomial distribution hangs on the outside, so the curve is underestimating. We're going to have to look at a technique to handle when the curve overestimates because there's gaps and underestimates because the bars exist above the curve. The way that we will handle this is with a continuity correction. The continuity correction will have us add or subtract the number 0.5 in our formula for the z-score. The reason it's called a continuity correction is because you're converting from a binomial distribution, which is discrete, to a normal distribution, which is continuous. So to correct the conversion from discrete to continuous, you use the continuity correction, which is plus or minus 0.5. I have some additional graphs here with different combinations of n and p to help you get an idea of how the parameters control the shape. Here in the first graph, n is 10 and p is 0.1. The graph is centered about the p of 0.1. That's where the highest peak is in this graph, the 0.1. And then from there, 10 is your number of potential outcomes. So you have observations 0 through 10. N times p would be your number of yeses. 10 times 0.1 is 1. N times 1 minus p would be your number of failures. So you could do 10 times 0.9, which would give 9. Or you could say, well, if there's 10 total, one person said yes, that means 9 people said no. Looking at this graph, it doesn't look like the normal curve fits over it very well. Do you notice right here, there's a huge chunk of space where the curve overestimated? Same thing right here. Big chunk of space in this position where the curve's overestimating. And then if you look here, the curve is underestimating where the bar is hanging out top. Same thing here, underestimation in all of these positions. There are special cases where we can handle the underestimation and the overestimation, but this particular graph isn't one of those special cases. As a matter of fact, if you check the assumptions, remember n times p was supposed to be greater than or equal to 10. And if we look at this, it is not greater than or equal to 10. Same thing with the 9, and it's not greater than or equal to 10. So we can't even use this for a normal approximation. You would have to work this problem out using only binomial distribution. Well, let's keep p at 0.1, but increase the sample size to 50. So we still have, so the graph is centered about the average, 50 times 0.1, n times p, that's 5. If there's 50 observations and 5 people said yes, that means 45 people said no. Or you could do 50 times 0.9, and that would also give back 45. If you notice, when you jump from 10 to 50, the number of bars underneath this curve increased drastically. But if you go by the assumptions, 45 is bigger than 10, that's good, but 5 is less than 10, so that doesn't quite meet the assumption. Now some textbooks use a cutoff value of 5. So depending on your book, this would be a maybe situation. If your book uses 10, you can't do it. If your book uses 5, you'll be able to work this out. So I'm going to go ahead and say binomial distribution only. But keeping in mind, if we had a textbook that was okay with an NP equal 5, and there are some out there, that we could use approximation on this curve. Let's get a curve that's a bit more centered. We'll let n be 10 and p equal 0.6. Multiplying these, n times p, we see that 6 observations were successes. 10 minus 6 is 4, so there were 4 failures. Or you could do 10 times 1 minus 0.6, 10 times 0.4, and that would also give back 4 failures. Looking at this curve, again, there's portions where the graph overestimates because of these gaps, and there's portions where the graph underestimates. According to our assumption, 6 is not greater than or equal to 10, and 4 is not greater than or equal to 10, so we still cannot work this out with the normal distribution. Again, this is binomial only. But if we were to increase the number of bars underneath this curve, if we were to bump 10 up so that we had a larger sample size, and there were maybe twice as many bars in here, then you would be able to work it out. Now the last case we're going to look at is an n equal to 50 and a p equal 0.8. Out of 50 people, 40 people said yes, that means 10 people said no. This is greater than or equal to 10, this is greater than or equal to 10. We've met both of these assumptions, we're set to go. And if you come in here and look at the graph, this looks like a pretty good fit. You can't really even visually see very many gaps left over. And the portions where the bars stick out above the curve aren't quite as drastic. So with this problem, you could use the binomial distribution, but if you'd rather take a shortcut, you could also use normal approximation. So here's the steps you're going to use to work out these problems. You're still going to follow the XZ table order for looking up probabilities. You're going to write it in terms of x being binomially distributed with parameters n and p, and you'll have to verify that you are indeed in a binomial situation. Then you'll check your assumptions. Remember, the assumptions are 10 successes, 10 failures. After this, you'll be ready to leave the x case and convert to the z distribution. To do this conversion, you need to remember that if x is binomial, you can also say that x is normal with parameters mu equal n times p and sigma equal the square root of np times 1 minus p. So when setting up the z-score, we're going to take an observation little x and subtract off the mean minus the np and divide by the standard deviation. Divide by the square root of np times 1 minus p. Now remember those gaps and bars that kind of hang over the normal curve? Right here where I'm talking about the bars that hang over and the gaps that occur here. What you can do is add and subtract multiples of 0.5 to accommodate for these. So to this number you're going to say plus or minus a 0.5. This is your continuity correction that allows you to go from a discrete distribution x to a continuous distribution, the standard normal distribution. This should have been plus or minus 0.5. You're going to add or subtract 0.5. After you write the problem in terms of z, you'll be ready to go to the table and look up your probability. What I want to show you next is a bit more detail on the continuity correction so you know when to add or subtract 0.5. So let's say you're looking at the probability of being less than some number a. You can rewrite this as the probability that x is less than or equal to a plus or minus that continuity correction. And it's going to be your job to figure out whether to add the 0.5 or subtract the 0.5 to accommodate. So let's say that our number a is the number 4, and we want the probability of being 4 or less. So we would be shading this portion of the normal curve right here. Now I'm going to have to erase this out so you can see what I'm doing, but just remember the only thing you would really be finding is under the normal curve, not all these bars. So let's see how we're going to handle this. This bar and this bar will cancel each other out. This one and this one will cancel each other out. This one and this one cancel each other out. So if you're looking all the way to infinity, they cancel. The only problem is that for the binomial distribution, To actually get the correct value, you also need this gap, because 4 is this entire bar height on the binomial. So what you've missed is this space right here. And you need to add that back in, plus the 0.5. So out of the a plus or minus 0.5, you're actually just going to add 0.5. Let's look at the next case. Being greater than or equal to 4 means that you would be finding this area under the normal curve for your approximation. Coming in and looking at what would cancel with what, let's start here. This underestimate and overestimate would cancel. The overestimate and underestimate here would cancel. The overestimate and underestimate here cancel. This gap here would about equal out with these two gaps that you're seeing right here. So we could say that this entire portion right here cancels each other out. This portion would end up canceling with the portion that you would have needed to add in, so that's okay. The only part that we really don't seem to be able to accommodate for is this part right here. So what you're going to have to do is subtract out that 0.5 that you couldn't accommodate for. So if you have a greater than or equal to, you're going to subtract out the 0.5. Let's say you're looking at the probability that x equals a specific number. Well, if you look at this on a normal distribution that z equals a number, we said that it always occurs with probability 0 for a continuous random variable. But for a discrete random variable, this actually has a value. For a discrete random variable, you're looking for the portion underneath the curve that's an entire bar height. So to actually get the value that you're looking for, what you're going to have to do is go to your number and say that your variable x is bound between these two numbers. And for the first number, you're going to have it on the lower end. So if a is 4, this number will be your lower end boundary. It would be 4 minus the 0.5, so a minus 0.5. And this number on the bar would be your upper end boundary, so it would be a plus the 0.5. So when you take the probability of equaling the number and add and subtract 0.5 and look at being the probability of being between these two, it'll give you the probability you were interested in finding. If you're looking at the probability of being between two different numbers, to subtract on the lower number and add on the upper number. Another way you could have thought about it, this one says x is greater because the big end is pointing toward it. This says x is greater than a, and we said that for greater you subtract. And this one, because the little end is pointing toward x, this one says that it's less than, and we already said that for less than you add. Each year, almost 5 million people are bitten or attacked by dogs. Children are frequent victims of dog bites. In fact, 60% of all dog bite victims are children under the age of 12. Let us say that a sample of 30 people bitten or attacked by dogs is selected at random from the population list. Let x equal the number of people in the sample under age 12 who were bitten or attacked by dogs. Let's find the distribution of x. We're thinking it's probably binomial. There's two outcomes. Either you were bitten or attacked by a dog, or you were not, yes or no. There's a fixed sample size of 30. There's a constant probability of success. 60% of dog bite victims are children under the age of 12. And there's independence. The chances that one child is bitten or attacked by dogs does not affect another child's chance of being bitten or attacked by dogs. Remember, this is a random selection of children across the country, not children in the same neighborhood near the same dog. Now that we know x's distribution, let's come in and read the question. Using the binomial distribution, so the true distribution of x, what is the probability that 3 or fewer people bitten or attacked by dogs were under the age of 12? We're looking for the probability that x is less than or equal to 3. This would equal the probability that 0 children were bitten or attacked by dogs, or that 1 child was attacked or bitten by dogs, or 2, or even 3 children were. Now let's go back and remember the binomial distribution formula. The probability that random variable x equals number little x is n choose x, p to the x, 1 minus p to the n minus x. Now we know we're going to have to work through this formula 4 times for the 0, 1, 2, and 3 x values. But let's go ahead and fill in what stays the same. First of all, we know that n is 30. The next thing that we see as constant is the probability of success. That's 0.6. And then the last thing we could clean up in this formula is that 1 minus 0.6 is actually 0.4. So from here, all we need to do is everywhere that there's an x, plug in the x value. So we'll plug in an x equals 0, 1, 2, and 3 into this formula where x is at. So I've gone through and plugged in. I kind of ran out of space to write it all in one line, so I did an arrow down here indicating dropping to the second line. This is the probability that x equals 0. This is the probability that x equals 1. This is the probability that x equals 2. And this is the probability that x equals 3. I'm going to type these values into my calculator and replace them by their decimal equivalents. I realized on this last one I actually accidentally wrote down 28. This should have been 27. 30 minus 3 is 27, not 28. So when you type this in, what you'll get back is this value. Now lastly, I'm going to take all 4 of these values and add them up to get the final answer. This adds up to the exact value below, which we could say is approximately 0. So the chances that 3 or fewer children are bitten by dogs are about 0. Let's rework this problem. What is the probability that 3 or fewer people bitten or attacked by dogs who are under the age of 12? But this time when we do it, let's use normal approximation to the binomial distribution. On the exam, you'll need to keep your eye open for this wording. If you work this out with the binomial distribution, when I told you to use normal approximation, you will not receive credit. To work this out, let's recall that we said x is binomially distributed with a fixed sample size of 30 and a constant probability of success of 0.6. We know that this is approximately equivalent in distribution to being normal, with parameter mu equal to n times p, which would be 30 times 0.6. That's 18. And standard deviation equal to the square root of n times p times 1 minus p. That would be the square root of 30 times 0.6 times 1 minus 0.6, 2.68. Now remember, we're only allowed to say that this equivalence is true under 2 conditions. The first condition we need is that the number of successes, or the average, is larger than 10. Here, 18 is definitely greater than or equal to 10. The second assumption we need is that n times 1 minus p, which would be 30 times 1 minus 0.6, is also greater than or equal to 10, which is true. So we can say that this approximation is valid and proceed. To work these problems out, we're still going to use our x, z, table steps. Let's think of the continuity correction. If I'm looking for the probability that x is less than or equal to 3, I'm actually going to have to either add or subtract the 0.5. So let's think back to those general rules. When there's a less than or equal to, you actually need to add 0.5. So when deciding whether or not to add or subtract, because of the less than or equal to, we're going to say plus 0.5. This means we're actually looking for the probability that x is less than or equal to 3.5. Now that we've written this in terms of x, let's convert to the z distribution. We can switch from x to z now and say that it's less than or equal to an observation of 3.5 minus a mean of 18, which came from here, divided by a standard deviation of 2.68. This gives back a z-score of negative 5.41. If you think of the normal curve, remember it's centered at 0 with standard deviation of size 1. And we said that anything beyond 3 and negative 3 would be considered an outlier. Negative 5.41 would fall right here, and the probability of being this number or smaller is practically 0. And again, just to show you on the table, the absolute largest z-score on the table is negative 3.94. If you're on the z-curve at negative 3.49, probability of being here and down is 0.002. So if you were to go even farther out on the tail to a negative 5.41, the probability of being here and down would be practically 0, even smaller than 0.002. Comparing these two answers, using normal approximation by converting from x to z to table, we got an answer of approximately 0. Using the binomial distribution, we got this exact answer, which is perfectly correct. But looking at it, we said, well, it's approximately 0. So these two methods produce the same answer. Using normal approximation to the binomial distribution, what is the probability that 15 to 19, inclusive, people under the age of 12 were bitten or attacked by dogs? This is the probability of being between 15 and 19 on the x binomial distribution. We'll need to add in that continuity correction at this point. Remember, the continuity correction is the value 0.5, and you have to decide whether to add or subtract it. You always want to subtract on the lower end and add on the upper end. So what we actually are looking up is the probability of being between 14.5 and 19.5. Well, we've made our continuity correction, but the other thing we need to do now is break it up so that you can look this up on the normal curve. Remember, the way we did this is we said, well, if you want to be between 19.5 and 14.5, what you'll do is find the probability of being at 19.5 and smaller. And then after this, you will subtract out the probability of being at 14.5 and smaller. When you subtract that out, it leaves over the portion you are interested in. So what we need to work out is the probability that x is less than or equal to 19.5 minus the probability that x is less than or equal to 14.5. This is now written in terms of x. We're ready to go to the z distribution now. To convert this to the z distribution, we'll take our observation of 19.5, subtract the mean of 18, and divide by the standard deviation of 2.68. Let's repeat this for 14.5. When you simplify, this becomes the probability that z is less than or equal to 0.56 minus the probability that z is less than or equal to negative 1.31. We've completed our z step. We're now ready to go to the table. I'll show you the table for the first one, and the second one I'll let you look up. We'll look up the 0.5. That's right here. And then we'll look up the 6, and that is right here. Coming in and lining these up, we see that these line up with the probability 0.7123. The second probability turns out to be 0.0951, and when you subtract these, it equals 0.6172, or about 61.72%, so we'll say about 62%. So we know the probability that between 15 and 19 children being bitten or attacked by dogs is about 62%. Here are the works cited for this lecture.